So if we're talking about friction, we know there's two kinds of friction. There's kinetic and static. Kinetic is for moving objects, and static is for objects that are standing still. So if I look at an example problem, first of all, this is going to be like a conceptual question. Let's say I have a block here. I'm actually going to, for the first time ever, draw a three-dimensional object, and hopefully it doesn't look too stupid. So there's my object. It's a block, and you're dragging it across the floor with force F like this, okay? And now I'm going to ask some scenarios, and I pretty much just want you to tell me if the frictional force is going to increase or decrease based on the following scenarios. So again, this is like a rough floor. It does have some kind of coefficient of kinetic friction, mu k, because there is friction. And I want to know, does the frictional force increase, decrease, or stay the same for the following scenarios? Okay? And once again, I'm going to give you the equation for kinetic friction. The equation for kinetic friction is equal to mu k times the normal force. In other words, the coefficient of friction times the normal force, which again comes from the surface on the object. And I want to know, how does the frictional force change for the following scenarios? What if, for part A, I double the pulling force, F. I double the pulling force, F. So now it can be 2F there. Okay? How does that change the kinetic friction? Now, if I pull it faster, conceptually speaking, the block is definitely going to move faster, but how does that change the frictional force? Well, let's look back at the equation, right? Because the frictional force equation tells us there's only two things that the frictional force cares about, and that's mu k, which only depends on how slippery the surface is. So if I'm on hardwood floor, this should probably slide pretty nice. If it's on ice, it's going to slide really nice. But if I'm on like a shag carpeting, this thing's going to have trouble moving. Or if I'm moving it across concrete, for instance, that's going to have a higher coefficient of friction, and it's going to be hard to move. But the fact that I'm pulling harder doesn't change mu k, because mu k only depends on the surfaces that are in contact with each other, not the pulling force. And then the normal force, well, the normal force only depends on the force of the surface on the object. And if we think of what's going on in the y direction here, this has a force mg going down and a normal force going straight up. And these two forces are going to balance each other out as long as it's not moving up or down on this surface, which it shouldn't be. It's not a flying box. It's also not a box tunneling into the ground. That'd be ridiculous. But if I double the pulling force, that's going to have no effect on the normal force, because the normal force really only cares about mg in this case, because that's the only force it's trying to overcome here in order to make it stand still on the ground in the y direction. In the x direction, it doesn't care. Normal force, I'm just going to look at y direction, because at the end of the day, that's what the normal force cares about. It cares about what's going on in the y direction. That's supposed to say direction. It looks like der, etion. Sorry about that, but you get the picture. So if I double the pulling force, it will not change the frictional force. No change. Okay? Now, part B, what if I put the box on its side? So in other words, what if I do this to the box? Now instead of dragging it like that, what if I now drag it like this, so that's pointing straight up, right? Like I'm decreasing the surface area between my surface and the box itself. How would that change the frictional force? I'll let you think about that a second. I really want you to think, if it does change it, does it cause this value to increase or decrease? And does it cause this value to increase or decrease? Because at the end of the day, that really determines what the frictional force is, these two components. Okay, so I'm giving you a second to think. You can pause the video, I'm going to get a nice drink of water here while you're thinking. That's some good stuff. And now you've had enough time to think, and I want to tell you that mu k does not change, and the reason being, you're not changing the surface itself or how slippery the box is. You're just changing what edge of the box you're putting it on. So the surface is still going to have the same amount of slipperiness. So mu k stays the same. Normal force, once again, if I were to draw a free body diagram, mg pointing down and normal force pointing up, you didn't change the mass when you rotated the object, and you definitely didn't change what planet you're on, g, which is what determines what g is. So the normal force is also going to stay the same. Because remember, normal force just balances out any forces going on in the y direction. So if mu k didn't change and the normal force didn't change, then once again, I should write no change instead of not change. But at this point I already wrote it, so I'm not going to change it. Okay, so that's parts A and B. And honestly, I feel like you get the picture here at this point, like of all the different things you could change. I mean, these are honestly the two biggest misconceptions I see. And if you can get your head wrapped around this, that's like a free, easy question on a test then that you now got correct. Okay? So that was a good conceptual question.